We've seen how a real sequence is defined, but it's also important to appreciate and understand that sequences are not always expressed as functions. And in fact, in this video, we want to consider three equivalent but different looking forms that sequences commonly take. The first form, which is called the explicit form of a sequence, is where we actually give the function for the sequence. And we've seen several examples of explicit forms of sequences in the past. For example, if we look at the geometric sequence, we know this is the general form for the geometric sequence, where A and R are just real numbers. If we look at the arithmetic sequence, we know this is the general form for the arithmetic sequence, where again, B and C are just real numbers. And these are the two that we've worked most with. However, there are many different types of sequences, and so let me introduce you to a simple sequence that you may or may not be familiar with. And this is called the oscillating sequence. This is a sequence where we have a base, negative a, where a is some positive real number, and we raise it to the nth power. Okay. And below the general form, I've just given a specific example of such a sequence, okay? Just choosing, some values for the parameters, okay? Now, the implicit form is where we're only given the first couple of terms in the sequence, but we're able to recognize the pattern and deduce the explicit form from it. So we can see what the general form for a geometric sequence could be. And if we look at our example where a is 1 and r is a half, we'd see it would be 1, 1/2, 1/4, 1/8, and we'd obviously be able to see the pattern. And we could deduce from the implicit the explicit form. The implicit form for an arithmetic sequence would look like this. And if we go back to our example where the first term in the sequence is 2, and then we keep adding 3 to successive terms in the sequence, we would get the following implicit form, and again, we could easily deduce the pattern and go back from the explicit. So we can go back and forth between implicit to explicit if the pattern's not too difficult for us to see in the first couple of terms. And of course, the oscillating sequence would have the following general implicit form. And if we put in a is equal to 1, we'd see we'd get a sequence of alternating signs, -1 and +1. Another very important form that sequences can be expressed in is sometimes called the recursive form. And this is where we have an explicit expression for xn plus 1, but it's not in terms of n, it's in terms of the previous terms in the sequence. And so here, if we looked at the geometric, the way we'd express that recursively is we'd say the first term in the sequence is a, and we get the nth plus 1 term by multiplying the nth term by r. And of course, for our specific example, the recursive form would look as it is below. The arithmetic, the recursive form would be, we have to specify the first term in the sequence, that would be our base b, and we'd say that we get successive terms, the xn plus 1 term, by adding c to the nth term. Okay. And again, for that specific example, the recursive form of the sequence would look as shown. For the oscillating, we would say that the first term was -a, and we got the nth plus 1 term by multiplying the nth term by -a. And again, if we look at the example, we would get something as shown. Now, why do we have all these different forms? The explicit form is very good when we want to study what we might call the asymptotic behavior of the sequence. In other words, what that means is we are trying to see what the sequence terms are doing as n's getting very large. Okay? We can see for the geometric, for example, that they're getting smaller and smaller and smaller, and they're approaching 0 as n gets large. We can see for the arithmetic that as n goes to infinity, as n gets large, the terms become infinitely large. The sequence basically goes to infinity. And we can see for the oscillating sequence what happens. As n gets large, the sequence just continues to alternate. It just flips back and forth between -1 and +1. So you notice that sequences can do different things asymptotically, and that's what makes them interesting. And we're going to talk in the next couple of videos about this problem in much more detail. Now the recursive form, it's not so obvious why we'd be interested in that, but this is a form that occurs commonly in iterative numerical techniques. An excellent example is when you do any sort of optimization. So if you're using Newton's method, steepest descent, anything like that, what are we doing? Well, we're starting off with a guess as to what the solution is, and we're putting it into some sort of algorithm, and the output is now our new estimate or our new best approximation of the solution. And we keep feeding that best approximation back into the algorithm and generating the next approximation. And in this way, we get a sequence of approximations that we hope, if our method is a good one, will converge to the true solution, will settle down to the true solution. And so these sorts of techniques are very, very common. And so the recursive forms occur a great deal, and they're very important. Next, we're going to talk about sequence convergence, what it means for a sequence to converge or for a sequence to diverge.